Thank you very much for the invitation. I'm very happy to be part of this celebration. And in fact, I'm going to say something about seeing something from, seeing the environment from a particle that I learned it from Raghu when I was a student. So hopefully I get to that part. So as the title suggests, I would be interested in Hamiltonian ODEs. Let me start off with the definition of what Hamiltonian ODE is. This is a very, very classical setting. You have a candidate for the energy. The energy is the Hamiltonian function. Is a function that, this guy. This is the Hamiltonian function. It's a function that is defined for vectors x. The vector x has the position part, q, in RD, and the momentum part, which is in RD. So this q represents positions of, in celestial mechanics, planets, stars, in statistical mechanics, particles. And p represents all the momenta. And the ODE is, and you may assume that the energy depends on time. And the ODE is given by this equation. The time derivative of q is given by the momentum derivative of h. And I'm writing h sub p for the vector that represents all partial derivatives with respect to various components of the momentum vector. And likewise, the derivative of momentum is given by another vector that is the partial derivatives. And it's more convenient to write an equation for the full vector x. The derivative of x now can be expressed as j. J is the matrix given by 0 identity minus identity 0 times the full gradient of h. So you should compare it to the gradient vector field that we have seen in this conference in several occasions. This is like the other extreme. So you take the full gradient vector field associated with the energy h, but you put this matrix J, and these are kind of, this is 2D by 2D matrix, and you have this D by D identity matrices sitting there. And the job of this matrix is somehow taking the full gradient vector field and swapping p with q and putting minus sign somewhere. So somehow you're doing the other extreme as opposed to the gradient vector field. And let me write phi th for the flow of this vector field. This represents the solution of this ODE, displaying the dependence of the solution to the initial data. So if the initial data is A, then phi HTA is that solution. And what is important is that this function phi that appears here, the flow, turn out to be a symplectic map, and that would be very fundamental. What symplectic means. You see, if you, maybe, you see, it's a shame I wouldn't write anything there, but this is an equation, maybe I should keep it somewhere. But you see, if you look at this vector field, because of swapping and putting minus signs somewhere, you immediately see that the vector field, this vector field is divergence free. If a vector field is divergence free, its flow is volume preserving. But if you think about it, there's more happening, there's more structure. Perhaps I should mention that when D is 1, then any divergence-free vector field can be written in this way. If D is 1, any divergence-free vector field can be written that way. But when D is strictly bigger than 1, there's more structure here. And the question is, can I take advantage of this additional structure? And in fact, the way to think about it is that if you write xi for one coordinate of position and one coordinate of momentum, if you look at this pair, then this vector field, if you ignore the other variables, is divergence-free even for this particular pair. So it's as if in dimension 2, you already have a divergence-free structure. This suggests that some kind of area should be preserved. In other words, you have more structure there. Instead of saying that the volume is preserved, additionally, you want to say that some surface areas is also preserved under the flow of the dynamics. And Poincaré figured out exactly what that means. As I mentioned, you can write down some two-form. The job of two-form is calculating surface areas, and that two-form is preserved under the flow. But let me give you an analytic way of describing what symplectic map is. If you look at this, I forget that I have this guy. I'm so bad with these things. My default way of giving a lecture is by chalk, and today I could not do it. So if I write A of x for the derivative of the flow, this is a matrix. This is a 2D by 2D matrix. Then this 2D by 2D matrix is going to satisfy this equation. So this matrix A times J times is transpose is J, or you can multiply both sides by J. The matrix J is in such a way that J squared is minus identity. So multiply both sides by A. What you learn is that the inverse of A can be expressed in terms of the transpose of A. So that's already a piece of good news, because inverting a large matrix is a mess, is a nightmare, but not if the matrix happens to be a symplectic matrix. So that's why that we should be able to put this to some good use. So again, if you compare it to gradient vector fields and solution to associated ODEs, Hamiltonian ODEs somehow is the opposite. For one thing, they tend to have many periodic orbits. So it's of interest to understand what periodic orbits are. And some well-studied questions in mechanics with applications in geometry, the so-called symplectic geometry, is that how many periodic orbits we have. Do we have periodic orbits? What the period is? And for example, if the energy is independent of time, the energy is conserved under the flow. So you want to look at one of the level set of the energy, and you're wondering how many periodic orbits exist on a given level set. So these are questions that are of interest. Give you a reason. Last week I saw a beautiful full moon, then was wondering whether I'm going to repeat the experience. Well, you do if you have a periodic orbit. But of course, you're interested in knowing what the period is, because you want to compare it to your lifespan. So that's why these are two fundamental questions. Now, let me be more focused today. Imagine that you have a Hamiltonian. Remember, Hamiltonian depends on x. X represents positions and momenta. And h may depend on time. But imagine that h is one periodic in time. And what I would like to study is how many one periodic orbits this guy has. It turns out that's a natural question, because Hamiltonian is already one periodic. So you're wondering whether you can find one period. And there's nothing special about one. You can replace it by any positive number. But maybe I should compare it to the scenario when you have a Hamiltonian that is zero periodic. What zero periodic means a Hamiltonian that doesn't depend on time. If Hamiltonian doesn't depend on time, then you may search for zero periodic solutions. But zero periodic solutions means constant solution, something that doesn't change with time. And then it's the trivial answer to the question. Namely, there's one-one correspondence between zero periodic orbits, namely the constant orbits, and the critical points of the Hamiltonian function. So there's one-one correspondence between such constant orbits and critical points of the function h. And something remarkable happens. It turns out that there is a lot can be said when you replace zero periodic with one periodic or positive period. And let me argue that if h is one periodic, then the vector field is one periodic. And remember, you're looking now for one periodic orbits. That means you start from a point A, you go for 1 unit, and you wonder whether after 1 unit you are back to the same place and repeat yourself. And in fact, if after 1 unit of time you're back to where you started, since the vector field is periodic, you're going to see the same vector field. Therefore, you keep repeating. So in order to have one periodic orbit for such a setting, it suffices to find the fixed points of time 1 map of your ODE. So remember, phi hx represents the time 1 map. This is where you are after 1 unit of time if you start from x. And if you're back to yourself, if you have a fixed point, then you have a one periodic orbit. So this suggests that for this classical problem, you want to study the fixed points of the symplectic map. And needless to say that I'm interested in the case that H is random. So let me see what randomness, how randomness can enter this game. So I want to have this Hamiltonian. I want to select it randomly, and I want to select it according to some translation invariant probability measure. So let me write script H for the set of Hamiltonian function one periodic in time, if you want. But since I reduced the problem to finding fixed points, I don't have to assume one periodicity anymore. So now you have this problem that you have a symplectic map coming from Hamiltonian ODEs, and you want to know how many fixed points it has. So you define the translation, and let's make a simple observation. So again, I'm writing fixed H for the fixed points of time 1 map. It's a little bit confusing, but remember that I'm interested in fixed points of the time 1 map. The simple observation is that if you translate the Hamiltonian, the set of fixed points also translates. So if you select H randomly according to an ergodic stationary probability measure, you produce this set in Euclidean space that is also random and stationary. And if generically, you expect this set to be a discrete set. And basically, what you have generically is this point process. And we want to develop some understanding about this random point process. That's what it boils down to. But first, the first question you may ask is whether I can calculate the density of this potentially discrete set. How you can talk about the density? Well, look at the fixed points of the time 1 map and count how many fixed points you have in a box of size 2L, kind of standard box. You take a box, a large box, and divide it by the volume. And it's not hard to show that this limit exists. This is some kind of law of large number. And the limit would be with probability 1 independent of H. And in fact, there's a simple recipe, not practical recipe, a simple recipe for calculating the limit. And the answer is that you just count how many fixed points you have in the standard box, this box. And that's a random set. That's a random number. You count how many fixed points you have there, and then you take the expected value. The expected value is exactly what you have for the right-hand side. But the problem is, in general, is not. But it turns out the examples show that in fact, you can kind of prove that for many examples that generically it is discrete. H identically 0. Well, this is a trivial example. Everybody is fixed. Yes. But so the right-hand side could be infinite. I'm not ruling that out. Yes, that's for sure. So then, the natural question is under what condition this number is positive. If it's 0, you're basically saying that I don't have periodic orbit. And is there a natural lower bounds? But this is the thing that I remember I learned it from Raghu when I was a student. It turns out that you should think of this as some Hamiltonian ODEs on the space of Hamiltonians. The way to think about it is that this Hamiltonian, you should think of it as the environment. In fact, you can write down examples of random Hamiltonian that looks like Lorentz gas. So you can start with some deterministic Hamiltonian, you translate it around according to some Poisson point process, and you add them up. So then you may wonder how the environment would look like seen from the solution to the Hamiltonian ODE. And that's kind of relevant intuition here, it turns out, as we will see later. So in other words, it's very relevant to define the following function. You see, I'm interested in the fixed points. You give me a Hamiltonian. What I do is that I start from point A, and I wonder whether I go back to A after 1 unit of time. But you can do it the other way around. Since the fixed point would be shifted if you shift the Hamiltonian, what you can do is that, you see, starting from A and having a fixed point starting from A is the same as starting from 0, but shifting the Hamiltonian instead. So because of that, the natural thing to do is the following. You give me a Hamiltonian H, I solve the corresponding ODE, but I insist that I start from 0. Then instead of saying, for what initial data I go back to myself, I come back to myself, it's more natural to ask for what Hamiltonian, 0 is a fixed point. That's kind of like the type of questions you want to address here. So this is the flow starting from 0 for a Hamiltonian. And then you shift the Hamiltonian for the amount, meaning that you go for, you start from 0, you arrive at psi t h, and then you look at h seen from this point. That would be the right thing to look at in this context. And one can show that this flow that you get here, the flow that see, I'm so bad with these things. Oh, here. Right, so this suggests that you define an ODE on the space of Hamiltonians. Okay, so now I want to give you a more reasonable formula for NP, because I want to study NP, I want to find lower bound. This is actually, this kind of questions goes back to questions in symplectic geometry and classical mechanics. So it's related somehow to Arnold's conjecture, that comes later. But for now, let me define the following thing. I want to define this operator that is the generator of the flow, the translations that you introduce on the Hamiltonian. So what I'm doing. So you give me a function defined on Hamiltonian is the space of randomness. You give me a function on the space of randomness. And I want to define this operator, which basically says translate H as much as S in direction EI. This is the standard vector, the basis for Euclidean space. And then differentiate with respect to S and set S equals 0. That defines an operator. You should think of it as a directional derivative in the direction that is associated with the flow. And I use boldface for this operator, the generator of the flow. And there's a typo here, ignore this. And then this psi, remember the psi, what psi does is that, again, you look at the Hamiltonian ODE, you start from 0, and psi says where you land after 1 unit of time. So you start from 0, solve the ODE, and then where you land. And since that depends on the Hamiltonian, you have a function. You have a function that is defined on H but takes values in R2D. Okay, so this is a typo. So if assume for now that this random variable h going to psi h, this is a function that is defined on the space of Hamiltonians and takes values in R2D. Let's say it has a density. This random function has a density I denoted by rho. Then, with some back of envelope calculation, you arrive at the following formula. This NP would be something like this. Is more or less a constant times the average of the determinant of the derivative, this this operator that I found for the generator, condition that psi of h is 0. Why I condition a psi of h equals 0? Because remember, psi h is where you land if you start from the origin. So you start from the origin, and you want to know where you land after 1 unit of time. But if you land at 0 again after 1 unit of time, that means 0 is a fixed point for your flow. So this set, psi h equals 0, the 0 level set of the function psi h, this corresponds to Hamiltonians for which 0 is a fixed point. That's what this set is. And then if you figure out, if you make sense of this conditional thing, then you have a candidate for NP. Though, again, it's not clear at all that this set is non-empty. In fact, having this set non-empty, or this set should be large enough so that you have a positive density for fixed points. Okay, so kind of, in some sense, what happens, again, going back to the function psi, oh man, you can imagine I'm so bad with these things. I always tell people I could have been born 100 years ago, my lifestyle would have been the same. So bad with technology. Okay, yeah. Yes. You see, lack of practice, what can I say? Yes, so you see psi is a function going from Hamiltonian into R2D. You have a probability measure on Hamiltonian, but you have to look at the support of this probability measure. Think of the support of the probability measure that we consider as some kind of a submanifold of this infinite dimensional space. Then the periodic orbits are related to the 0 set of this function. This function takes values in R2D. So generically, you expect the level set would be a submanifold of codimension 2D. So you basically performing this integral over a space that is of codimension 2D. And what that manifold is, that would be exactly the question here. But in order to give a better meaning to the formula that I mentioned, I should review some examples. Let me start with a trivial example. One example of this stationary probability measure is that you start with a periodic Hamiltonian. So now the Hamiltonian is periodic also in the space variable. Every coordinate of x is also, h is periodic there. So you start from h0 and then translate h0. If you translate it, since this guy is periodic, after 1 unit of time in every coordinate, you're back to where you started. So if you think about it, this space, the orbit of this Hamiltonian isomorph is isomorphic to a circle, to a torus, 2D dimensional torus. And you can put the Lebesgue measure here, and that gives us an example of a stationary process on the space of Hamiltonians. Though the support of this probability measure that I have in mind here would be simply the translates of h0. And this is kind of like as if you're not dealing with a random situation at all. So let me make it more sophisticated. So now I want to play a somewhat different game. Namely, I start with a Hamiltonian. See, previously, my Hamiltonian was defined in R2D, but now I define it in R to power n. N potentially is strictly bigger than 2D. And I assume this Hamiltonian is periodic in every coordinate, this Hamiltonian. And then I take some matrix, which is n by 2D. And then, you see, since K is periodic, in some sense, K is defined on n-dimensional torus. So think of K that is defined on n-dimensional torus. So take a point on that torus, I denote it by omega, but I think of it as this box with 0 equals 1, and form this Hamiltonian function. So you give me an omega on the torus. Then I can define a function in R2D by this recipe. And what I'm doing here is that, you see, my function is defined on Rn. The job of this matrix A is turning a vector in R2D to a vector in Rn, so that I can add this vector to omega, and then this Hamiltonian makes sense. So take this set of such Hamiltonians. So out of K, I'm going to build these collection of Hamiltonians and put probability measure on it, which means I have to put a probability measure on torus, and I choose Lebesgue. And one can show that indeed this is a translation invariant probability measure on the space of Hamiltonians. And in order, oh, yes, this is, I'm sorry, this is like too low. You can make this probability measure ergodic by assuming that the columns or rows of this matrix A, somehow there is no rational dependence between them. So that's why you have the.
What is your H sub 1 here?
Oh, that's a typo. I'm sorry. This is OK. So OK, yes, I apologize. This is a typo. So, so on, you have a family of Hamiltonians. They put probability measure here, which is just Lebesgue on the torus. And this guarantees the ergodicity. You don't want to have any kind of rational dependence between various columns. And let me tell you how the formula looks like in this setting. Then NP would be given by this recipe. So let me explain this formula. So what happens is that now the map, which is of interest, the psi of H omega is a typical Hamiltonian you have. What it really says is that for each omega on the torus, you have this Hamiltonian. You start from 0, and you figure out where you land after 1 unit of time. This is why psi omega. So the periodic orbit corresponds to the 0 set of this function that is defined on this n-dimensional torus. So this generically would be a manifold of dimension n minus 2d, because psi is a function from n-dimensional torus to Euclidean space R2d. So the 0 set of that would be of codimension n minus 2d, the codimension 2d, so the dimension is n minus 2d. So this is a submanifold of this dimension. Take the surface measure on there, and then this is the expression that you get for. This is a consequence of area and co-area formula. At the top is something that appears if you're familiar with something called Katz-Rice formula. But the bottom has to do with the fact that Katz-Rice formula is in Gaussian setting, but here I'm doing quasi-periodic setting. That's why you have a completely different expression. So this is a candidate for this conditional probability measure I discussed before. I've kind of written down a formula for the conditional distribution. Okay, so by the way, any questions so far? And you can also consider the almost periodic setting. You start with some Hamiltonian on Euclidean space. You look at all the translate of that Hamiltonian. And if this set happens to be pre-compact, then we say we have a quasi-periodic Hamiltonian. And you take the topological closure, and the standard thing says that you can turn it to a topological group. And you can take the Haar measure on that topological group. That would yield an example. So in other words, the support of this stationary probability measure would be the closure of the translates of some fixed Hamiltonian. And in this case, in some sense, the randomness, the support is isomorphic to a torus, but with possible dimension infinity. So what happens is that in some sense, the space of Hamiltonians is this infinite dimensional manifold. But if you go to quasi-periodic, the support would be still finite dimensional and is isomorphic to this n-dimensional torus. But if you go to almost periodic case, you still have the compactness. You have some infinite dimensional torus, but the finite dimensionality is lost. And of course, you can go on and have more complicated stationary process. But let me mention some rough description of some of the results that one can prove in this setting. And is that indeed, we can prove such formulas are true in the quasi-periodic setting, and I think with some extra work, one can push it to almost periodic setting. However, if I want to go beyond almost periodic setting, almost periodic setting is the least random example of stationary processes. If there's a spectrum of randomness, that would be the least random case. But you can have far more chaotic dynamical systems that you can prove similar results. But unfortunately, with the techniques that I can use here, I have to assume that H is small. Or if I express things in terms of the time one map, the symplectic map that I have, which is the time one map of the Hamiltonian, if H is small, that means the symplectic map is sufficiently close to the identity map. So if that is the case, then I have additional results covering other stationary processes. So far, so good. Okay, but let me give some history of questions that have been interests in classical mechanics and symplectic geometry. That was my original motivation for formulating this kind of questions in random setting. So for that, I have to talk about symplectic manifolds. So what's happening is this. So you started with Hamiltonian ODEs coming from classical mechanics. Then Poincaré discovered that some sort of area is preserved. And we managed to appreciate that property and discovered many things about Hamiltonian ODEs, understanding the meaning of the invariance of this area form. Now, you can do it the other way around. You can start with an arbitrary manifold, put a two-form, some kind of area notion on that manifold, and then one can find a class of vector fields for which that area is preserved. So you can do it the other way around. And so a manifold equipped with such area form, this is a two-form, is called symplectic manifold. And you should think of this, for example, Euclidean setting is as if this matrix J is replaced by some anti-symmetric invertible matrix. So we kind of a generalization of all those vector fields that I discussed before. And what happens is that you give me an arbitrary Hamiltonian function H, I can find a vector field for which the area is preserved. And this is the analog, the generalization of Hamiltonian ODEs for general manifolds. Then you can talk about the time one map. And again, if H Hamiltonian function is independent of time, you can talk about constant orbits, and they correspond to the critical points of the Hamiltonian function. And it turns out that you can study the critical points of arbitrary functional manifold using algebraic topology. So there are all these technologies from topology that would allow you to say something reasonable about critical points of such function. And again, you're interested in time one map and fixed points. And in fact, Arnold conjecture addresses such a question for a manifold that is closed without boundary. And somehow what I'm doing has to do with replacing this closed compact manifold, this closed manifold, with the space of Hamiltonian, which is infinite dimensional. And I'm hoping by using ergodic theory, I can make up for the lack of compactness. That's basically the way to think about it. So you have a Hamiltonian function defined on a manifold. You look at you solve the corresponding Hamiltonian ODEs. You look at the time one map, and you want to know whether the fixed point is a non-trivial set. And you want to have some a sharp lower bound on the number of fixed points of such Hamiltonian. And it turns out there are things that you can do. You can measure the topological complexity of the manifold. There are different ways of doing this. One of them is called cup length of the manifold. And that gives a sharp lower bound on the number of fixed points. So my attempt was to extend this kind of developments in the random setting. And I should mention that this is related to something called Lusternik-Stellermann theory, which basically says that if you have scalar-valued function f on a manifold, then you have a universal sharp lower bound on the number of critical points, meaning a lower bound that is independent of f, because you see the left-hand side is independent of the choice of Hamiltonian. That's the significance of this inequality. And what you are saying is that Arnold conjecture says that there is a variant of this that is true for fixed points. And there's the so-called more theoretical version of this theory when this sharp lower bound can be improved, and that has to do by studying the homological groups associated with the manifold. The rank of those homological groups would give sharp lower bounds on the fixed points. Okay, so what is the history behind Arnold's conjecture? The reason that I mentioned is that the tools that people have developed, which is mostly elliptic PDEs, system of elliptic PDEs, these are the tools that I use for handling the problem. So the problem looks like an innocent problem, but it turns out that it's highly non-trivial and is responsible for many, many developments in symplectic geometry. Yes?
At least in the context I understand the most theory and counting the loop typically for the random functions, we're interested. The lower bound, the deterministic lower bound are irrelevant because typically the random things have many, many more critical points than what the lower bound gives. So,
You see, that's very true, because my formulas, you see those integrals, they are capturing what you're saying. So what's happening is that basically, you see, in this setting, because of compactness, you're looking for these isolated points generically. But for Euclidean space, when you formulate it this way, you're looking for this submanifold that is sitting there. And then all these critical points, all these fixed points, they come for flowing according to Hamiltonian and hitting this set. So you see, these lower bounds are integers. And integers would be irrelevant for our setting. You're basically doing ergodic theory. And the best you can hope for is that you put conditions on the type of fixed points you have, and you just want to say it has a positive density, and you want to get some lower bound on the lower bound on that the set of the density of fixed points. That's the best you can hope for. But so I'm not using any of these theorems, but I'm using the way they prove it. That's how I do it. No. Otherwise, this kind of things would be irrelevant. Yes, I totally agree with you. But I need to review but he's responsible. You asked me a long question. So 1 minute. Okay, I do my best. So yes. So I want to mention that the major breakthrough was achieved by Floor, who, yes, I mean, I'd better go very fast. So what happens is that you can define this action. So what is the analog of, you see, to do this, you basically look at the action functional associated with this Hamiltonian, which is you start with a loop, and you calculate the corresponding action. This is the functional defined on loops, and critical points of this action functional corresponds to periodic orbits. And you calculate the derivative of it. Let me kind of get to this point. And you set up the gradient flow associated with this action functional. So you want to find a periodic orbits, but then you run the gradient flow, which means you start with a loop. You don't know if this is the periodic orbit you're looking for or not. You start with a loop, and then you evolve it according to this gradient flow. That would traces out a cylinder, topologically speaking. And this cylinder presumably connects two periodic orbits. This is what Vadim was discussing yesterday, but in infinite dimension. So you look at the connecting orbits between these cylinders. But these cylinders, when you write it down, let me just get to Oh man, I was too ambitious. You see, I told you I'm not good at this. So when you write down the equation for gradient flow, you end up with this system of elliptic PDEs. This is, if you pretend J is I in complex numbers, which is exactly what J is doing, multiplying things by I. This is Cauchy-Riemann operator, and this is a perturbation of that. You solve this elliptic PD in order to find those critical points, the asymptotic behavior of solutions to this. So this is the function of two variables. This is the way you parameterize that cylinder. And then the analysis of this system of elliptic PDEs is how you prove the existence of such periodic orbits. Maybe I stop.